Okay, so we're not going to write all this down. We did this with second hour, so I want you guys to appreciate Newton's method here and what Newton would do by hand, so you can appreciate what we're able to do with the calculator a little bit. Okay, so cube root of 11. What would be the function that would give you a solution to cube root of 11? X cubed minus 11, right? And the derivative of that is 3x squared. Now we chose to make a guess of 2. And so as we use Newton's method, x minus x cubed minus 11 over 3x squared, we actually computed this by hand. We put a 2 in for the x, and we got 2 minus 3 over 12, which came out to 2 and a fourth, or 9/4. And we said, well, maybe if we took 9/4, or 2.25, and we raise that to the third power, maybe we'll be close. Is it better than 2? Yeah, it's better than 2, but we're still off, aren't we? So then after that, what will we plug in next? We plugged in 2 and a fourth, or 9/4. And we got 9/4 minus 729 over 64 minus 7 over 4 over 64 divided by 3 times 81 over 16. You can see our work with our fractions, and we came up with 1,081 over 46. Now we'll try that. We'll take 1,081 divided by 486. So Newton was able to say, I'm going to express it as a rational number. So it's a rational number. Now I'm going to cube it, and do I get close to 11? So he could come up with rational numbers that were excellent approximations for these irrational numbers. And if you're not satisfied with that, well, he could do it again. You know, again, the question was, when do you stop? Well, when you say, you know what, I'm close enough. And maybe being to the nearest hundredth, maybe that was close enough for Newton, but he can make that decision. So why did I show you guys that? Number one, I want you to appreciate that it's a little bit more challenging to do it by hand, isn't it? Second of all, every year I have students who they kind of speak up. They're like, well, this is stupid. You said we couldn't use our calculator, but yet we're going to use our calculator. Well, we're going to use Newton's method, but we're just going to cheat a little bit by using calculator. If you don't want to use the calculator, we could do it all by hand like this. Okay, Spence says no. All right, then what I need you to do is this. I need you, in example 2, to draw this general shape that you see here, okay? It doesn't have to be perfect, but we want to be close. You're going to have tick marks for 1, 0, 1, 2, 3, 4, 5, okay? Your function should cross at 2. It should have a local minimum here at 3, and then just kind of do that behavior as you head off towards 4 and 5. And we'll pick up with that when you guys. Okay, do you have the shape drawn? Okay, so I think that probably 95% of the students who go on and take this test, they understand the basics behind Newton's method and the calculation of, say, the cube root of 11, like we showed up above. This is where they start to fall apart, and I don't understand why. Like, I can't understand what people don't get about this next section. So if you don't understand something, you've got to ask me. You got to pause me and help me kind of figure it out. We got it? All right. So this is a graph of a function. How many zeros or solutions does this function have? 1. Where does it happen? At 2. So if we use Newton's method, we would like to come up with that solution of 2. Watch what happens if we make certain guesses. Let's guess 0. To do Newton's method without using the actual equation, but using the graphical approach, once I guess 0, what would you then do? What's the next step? Find the point, take the derivative, draw a line that's tangent, and then what? Look for the x-intercept. So did that bring me closer to 2 or further away from 2? Brought me closer. If I want to get it, I could do it again, right? And I would, eventually I'd come up with that value of 2, would I not? Okay. All right. So what? Who knows? Let's guess 1. We arrive there. Draw a line tangent. Which spot do we look for the tangent line? The x-intercept. Does that bring me closer or further away? Brought me closer. I guess again. You can see before long, I'm right on top of 2, aren't I? And so we get that answer. So if you guess 1, you get 2. What if I guess 3? I guess 3. And so I find the location on the curve. What do I do then? Draw the tangent line. Is that tangent line ever cross the x-axis? Because it has a slope of 0. So your next goal is to locate where it crosses the x-axis, but it doesn't. Think about Newton's method, you guys. X minus f of x divided by f prime of x. Your guess was 3. 3 minus some function value, we'll say -1, divided by the derivative. What's the derivative? 0. You see how you're going to get an undefined value or an error if you guess? If you guess positive 3 in that situation? So when we talk about guesses, Jake asked an excellent question before. Can you guess, behind it or in front of it? The answer is yes, but you could guess 2.5, but you couldn't guess 3. So depending on looking at the function, there's some behavior that you have to account for there. Look at 4. This is where people really get confused. I guess 4. I find the point. What do I do then? Line tangent, and I look for the x-intercept. Did that draw me closer to or further away? Further away. Let's try it again. Punch in next value. Draw the line tangent. I'm going further away again. I try it again. So what's going to happen to it? It's going to go towards infinity. And the same thing would happen with 5. No. No. Okay. So we'll try to clarify those and put them together as we look at example 3. And that's use Newton's method to find all the roots of the following polynomial to 4 decimal places. Okay. So we're going to make sense of it all right here. How many real solutions could this polynomial have? It could have 3. It maybe only has 1. Maybe it looks something like this, okay? But it could have 3. So suppose it has 3. I'll just draw a shape here. Okay. Suppose it crosses 3 times. What part of the graph would I not want to guess at? Wherever the local minimum is and wherever the local maximum is. Agreed? Where do those happen? How would we find it? You take the derivative, set it equals 0. What's the derivative? 3x squared minus 2. So 2 equals 3x squared. 2 over 3 equals x squared. So plus or minus the root of 2/3 is equal to x. Now I'm not even going to come up with a decimal approximation for what the square root of 2/3 is. I will pretend we're like Newton in this situation. We don't really care exactly what that decimal approximation is. We just want to use it for a guess. We know that this spot here happens at the root of 2/3, and it is a negative value. We know this spot happens at positive root of 2/3. Can you give me a number to the left of negative 2/3? Would you all agree that -1 is to the left? So we'll just make -1 our guess. Could you give me a number to the right of 2/3? Root of 2/3. 1. Could you give me a number between negative 2/3 and positive 2/3? Yeah, sure. Yep. A fourth or 0. Yep. Yep. Okay. So what I'm going to do is I'm going to make those my guesses. So I'm going to find these solutions without using the second calculate option on my calculator. I'm going to use Newton's method. Newton's method says x minus that guy, x cubed minus 2x plus a half divided by what? 3x squared minus 2. Newton's method says do that. So I'm going to type that into my calculator. Right, but then we wouldn't understand what Newton's method is doing, right? So we've got x minus parentheses, x cubed minus 2x plus 0.5 divided by 3x squared minus 2. And I go to my table, and what do we want our first guess to be? -1. -2.5. You see it kind of jumping around right now, and you're not real confident of what it's going to do. It's doing that graph thing that we were doing on the other problems. Let's see when it finally kind of hones in on one value. -1.896. Is that getting better? -1.609. -1.531. -1.526. Looks like -1.526 is probably a really good approximation for this value, isn't it? Kelvin, what would you like to guess now? All right, we'll do it. 0, I get 0.25. All right, we'll guess 1/4. 0.25, 865. Looks like 0.25, 865 is a really good approximation for that middle one. And now I'll guess 1. He's always a step ahead of us. That's just part of being around greatness. Now, I typed in 1.267, but you can see if you actually highlight this, it's 1.267035. So, you know, when you highlight that, it can give you a little bit more of a decimal, 1.267035. And you can see that you come up with some good values. Now, I'm going to end with this last piece here. If I type in x cubed minus 2x plus 0.5, and I go to my graph, zoom 6, I want to find this spot right here. I'm just going to find one solution. So I can calculate 0. Now, you said it was going to be between what two values? 0 and 1. So I'm just going to make sure that I'm between 0. So x, okay, fine. And then I'm going to move over. Or you said that you wanted a guess of 1, right? So I've moved somewhere past that. And you can even type in, you can say 1 for a guess. And it will start at 1. You can see it comes up 1.267035, exactly like we had. So your calculator uses Newton's method every time it does that. And that's what I want you to understand. That's it. You guys have the back side of your worksheet. And I'll get that answer key up. I do have the answer key set to go for applications of business and economics. You only have 3 worksheets. You have a study guide. You have a test on Wednesday, which means Monday and Tuesday you're going to have time to work on those. The study guide, I do have the answer key done. That should be up online. This one I don't have done yet. But the front page should be very easy to check, right? Just take the value and square it or cube it or whatever. Yeah, I thought I handed those out today, didn't I? Oh, okay, I have them up here, I'll hand all that out. I didn't, last hour I did at the beginning of class, I'll do it right.